Pick up a teaspoon. You have done it 1,000 times, and your body knows exactly what a small object is allowed to weigh. Now imagine a single teaspoon that weighs 1.4 trillion kilograms, more than a mountain range, more than every car in a large country combined. Your instinct says that is impossible, that matter simply does not come that heavy. But that instinct is wrong, and the reason it is wrong carries us through the most extreme objects in existence. Somewhere out in the galaxy, right now, there are stars heavier than our sun, crushed into balls no wider than a city, so dense that a spoonful would tear straight through the Earth. They are made of the same neutrons sitting inside your own atoms, simply packed together with all the empty space removed. And there is a strict limit set by physics itself on how much of this matter can gather before it stops being a star and becomes something far darker. Make yourself comfortable. Subscribe if you're new here, because by the end of this, your sense of how heavy a small thing can be is going to be quietly, permanently overturned. Let's slowly settle into this. Part 1. The question a child could ask. There is a question that almost everyone has wondered in some quiet form, usually as a child, usually without ever realizing that it leads somewhere extraordinary. The question is this: what would happen if you built an object out of nothing but neutrons? Those tiny, neutral particles tucked away inside the nucleus of every atom. Could you make a neutron tennis ball, a neutron football, a neutron mountain? And if you could you just keep going, adding more and more neutrons, building something ever larger, with no ceiling and no limit? Or does the universe, at some point, quietly say no? Hold on to that phrase, because it is going to follow us through everything that comes next. Just keep adding more. It sounds so innocent. It sounds like stacking blocks, like piling stones, like filling a jar one grain at a time. And for most of human history, that is exactly how building has worked. You want something bigger, you add more material. There is no hidden rule that says a wall can only be so tall or a pile can only be so wide. The world of everyday objects is forgiving that way. So, when we ask whether we could build an ever larger object out of pure neutrons, our instinct whispers back, of course, why not? Just keep adding more. But neutrons are not stones, and the nucleus of an atom is not a quiet place. The answer to this simple question turns out to be equal parts subtle and marvelous, and reaching it carries us straight through the three great pillars of modern physics. We will need quantum mechanics, the strange rulebook that governs the smallest things. We will need the nuclear forces, the powerful and short-tempered forces that hold matter together at its core. And we will need gravity, the force we feel every second of our lives and yet understand the least. This is a story where imagination and reality collide, where space-time itself begins to bend, and where the familiar laws of physics get stretched until something unrecognizable steps out of the wreckage. Let us begin, as every good investigation does, with the suspect at the center of it all. What exactly is a neutron? As you probably know, at the center of every atom sits the atomic nucleus, a dense little knot of matter that holds almost all of the atom's mass in a vanishingly small space. Inside that nucleus are two kinds of particles. There are protons, which carry a positive electric charge, and there are neutrons, which carry no charge at all. That is what the name is telling you. Neutral. A neutron is electrically silent. It does not push, and it does not pull, on anything around it through the electric force. And that silence is the first clue, because at first glance it makes the neutron sound useless. If a neutron does not electrically attract or repel the protons sitting right beside it, and does not even electrically interact with its fellow neutrons, then what is it actually doing in there? Why does nature bother to pack these neutral, seemingly inert particles, into the core of every atom heavier than the simplest hydrogen. It would be easy to assume they are just filler, dead weight riding along inside the nucleus. But that assumption could not be more wrong. The neutron is not filler. The neutron is the quiet reason the nucleus does not tear itself to pieces. And, to understand why, we first have to understand the violence it is holding back. Because here is the thing that almost no one stops to consider about the ordinary matter all around you. The chair you are sitting in, the floor beneath it, the very atoms of your own body are not calm. At their centers, they are sites of a permanent, barely contained war. Every nucleus that contains more than a single proton is a place where powerful forces are locked in a standoff, where attraction and repulsion are balanced on an impossibly fine edge, and where the slightest imbalance can mean the difference between a stable atom that lasts forever and a radioactive one that falls apart. We tend to think of solid matter as the very definition of stillness and stability. It is, in truth, a kind of frozen battle, and the neutron is one of the most important soldiers in it. Before we go any further, it is worth pausing on just how strange and how empty the inside of an atom really is, because it changes how you think about the solid world around you. The nucleus is almost unimaginably small compared to the atom that surrounds it. If you were to scale up a single atom until it was the size of a large sports stadium, the nucleus sitting at its center would be no bigger than a pea resting on the very middle of the field. Everything else, the entire volume of the atom out to its edges, is the thin haze of electrons, and between them, essentially nothing, empty space. Which means that the matter you think of as solid, the table, the floor, your own hand, is more than 99.999% emptiness. The reason your hand does not pass straight through the table is not that the two are solid in any ordinary sense. It is that the electric fields of their electrons push against each other. In a very real way, you have never truly touched anything in your life. You have only ever felt the push of one electric field against another. And tucked into that tiny pea at the center, that nucleus holding nearly all the mass of the atom, sit our protons and our neutrons. The neutron itself was the last of the three basic building blocks of the atom to be found. The electron was identified at the end of the 19th century, and the proton not long after, but the neutron stayed hidden until the year 1932, when the physicist James Chadwick finally proved it existed. It had eluded discovery for so long precisely because of the property that defines it. It carries no electric charge, which makes it nearly invisible to the experiments that hunt particles by their electrical pull. The neutron is the quiet one, the particle that does not announce itself, slipping through detectors that would have caught any charged thing instantly. And yet, as we are about to see, this silent, uncharged, easily overlooked particle is one of the most important objects in the universe. Without it, the cosmos would contain almost nothing but hydrogen. Every heavier element, every atom that makes up the world you know, depends on it. There is one more thing about the neutron worth knowing before we continue, because it adds a quiet tension to everything that follows. A neutron is not truly fundamental. It is itself made of smaller particles called quarks, 3 of them bound tightly together, and that internal structure gives the neutron a curious instability. A neutron locked safely inside a stable nucleus can last essentially forever, but a neutron left entirely on its own, floating free outside any nucleus, does not last at all. In about 15 minutes, on average, a lone neutron falls apart, decaying into a proton, an electron, and one of those ghostly neutrinos we will meet again later. This is a strange and important fact. The very particle we are proposing to stack into a giant object is, when isolated, fundamentally unstable, prone to transforming itself into something else within minutes. So part of the challenge of building anything from pure neutrons is not just holding them together against the forces we have discussed, but holding them together tightly enough and quickly enough that they remain neutrons at all. Keep this in the back of your mind. It will matter enormously when we finally understand what it takes to bind neutrons into something permanent. So, before we can answer our innocent question, before we can find out how many neutrons we can stack before something gives way, we have to look closely at that war. We have to understand what the protons inside a nucleus are doing to each other and why, by every reasonable expectation, the nucleus should simply explode. Only then will the role of the neutron and the strange limits the universe places on it start to make sense. So let us shrink down, past the surface of ordinary matter, past the swirling cloud of electrons, all the way to the cramped and crowded interior of a single nucleus, and see for ourselves what is really going on in there. Part 2. The war hiding inside every atom. Imagine two protons sitting next to each other inside a nucleus, separated by a distance of about 1 femtometer. That word may be unfamiliar, so let me put it in scale. A femtometer is 1 quadrillionth of a meter, written as 1 times 10 to the minus 15 meters. It is to a single meter roughly what a marble is to the distance between the Earth and the Moon. This is the typical separation between particles packed inside an atomic nucleus, unimaginably small. And it is at this scale that the first force in our story reveals just how fierce it is. Both of these protons carry a positive electric charge, and one of the oldest rules in physics is that like charges repel. The strength of that repulsion is described by Coulomb's law, which states that the force between two charges is proportional to the product of those charges and inversely proportional to the square of the distance between them. The closer they are, the harder they push apart, and because the distance is squared, that pushing grows ferociously as the gap shrinks. When we take two protons, each carrying the fundamental unit of electric charge, and place them 1 femtometer apart, and we work through the arithmetic of Coulomb's law, we arrive at a number. The repulsive force between them is roughly 230 newtons. Now, 230 newtons might not sound like much. It is a number from a physics problem, abstract and weightless, so let us make it real. 230 newtons is the force you would feel holding up a mass of about 23 kilograms here on the surface of the Earth. Picture yourself standing in an airport. In front of you is a large suitcase, fully packed, the kind you are not entirely sure is under the weight limit. You reach down, grab the handle, and lift it straight out to the side, holding it at arm's length, your arm parallel to the floor. Feel the strain in your shoulder, the ache building across your forearm, the slow burn of the muscle fighting to keep that case from dropping. That is what 23 kilograms feels like when you hold it away from your body. Now hold that feeling in your mind and shrink it down. That same straining force, the full weight of that loaded suitcase pulling against your arm, is the force two protons exert on each other when they sit 1 femtometer apart. Two specks of matter, each a quadrillionth of a meter across, each so small that 100 trillion of them would not cover the period at the end of a sentence, are shoving against each other with the strength it takes to hold a packed suitcase out at arm's length. The repulsion inside a nucleus is not gentle, it is colossal. There is a reason we almost never notice this hidden ferocity, and it is the same reason it took humanity so long to discover it. The repulsion is enormous, but it acts over a distance so impossibly tiny that its effects never reach our world directly. The whole struggle is sealed inside a region, a quadrillionth of a meter across, locked away beneath the calm surface of ordinary matter. We walk through life, surrounded by these contained explosions, billions upon billions of them in every speck of dust, and we feel nothing, because the war is perfectly balanced and perfectly hidden. It is only when that balance is disturbed, when a heavy nucleus finally loses its grip and comes apart, that the hidden energy leaks out into our world. We call that leak radioactivity, and in its most dramatic form, when we deliberately force many heavy nuclei to break apart at once, we call it nuclear energy, or a nuclear weapon. The almost unimaginable power locked inside the atom, the power that lights cities and that has threatened to end them, is nothing more than a small fraction of this nuclear war being released. The force is always there, in every atom, held in check. We have simply learned, in a few cases, how to let it out. And this is where the war becomes clear. A heavy nucleus does not hold 2 protons. It holds dozens. Uranium holds 92 of them, crammed together in that same tiny volume, every single one of them pushing violently against every other. The total repulsion inside such a nucleus is staggering. A storm of electric force all pointing outward, all trying to blow the thing apart. By the plain logic of electromagnetism, no nucleus with more than 1 proton should exist at all. The moment you try to bring a second proton close, the repulsion should fling it away, and yet nuclei do exist. They are stable. They sit at the centers of the atoms in your body and have done so, in many cases, for billions of years without so much as flinching. Something is holding them together against that immense outward push. Something is winning a fight it has no business winning. It is worth dwelling on the reason that repulsion is so vicious at these distances, because it comes down to that squaring in Coulomb's law. The force grows as the inverse square of the distance, which means that as 2 protons are pushed closer together, the repulsion does not just rise, it explodes. Halve the distance between them, and the force quadruples. Bring them 10 times closer, and the force becomes 100 times stronger. So when you try to assemble a nucleus, forcing protons into a space a quadrillionth of a meter across, you are climbing the steepest part of that curve, where every tiny step inward is met by a ferocious surge of resistance. The protons are not merely reluctant to be near each other. They are fighting it with everything they have, and the closer you push them, the harder they fight. Building a nucleus is like trying to press the north poles of 2 powerful magnets together, except the magnets get exponentially stronger the closer you bring them, and you are working at a scale where the push of a loaded suitcase comes from objects too small to see even with the finest microscope ever built. Now multiply that across an entire nucleus. In uranium, 92 protons are crammed together, and every one of them is repelling every other one of them, all at once, all the time. The total outward push is not 92 suitcases. It is far worse, because each proton feels the combined repulsion of all 91 others. The interior of a heavy nucleus is a place of almost incomprehensible electrical violence, a storm of outward force so intense that by the plain accounting of electromagnetism alone, the thing should detonate the instant it forms. And here is what should genuinely unsettle you. That storm is raging right now in the nuclei of the atoms that make up your chair, your walls, the device you are listening on, your own body. The solidity and the calm of the physical world is a surface illusion. Underneath it, at the center of every heavy atom, a war is being fought every moment, and has been fought without pause since those atoms were forged. The stillness of matter is not the absence of conflict. It is conflict held in perfect, permanent balance. There is a beautiful irony hidden in all of this that is worth naming. The electric force, the one tearing the nucleus apart, is the same force that, on the everyday scale, builds the world up. It is electromagnetism that binds electrons to nuclei to make atoms, that binds atoms together into molecules, that holds together every solid object you have ever touched. The chemistry of life, the strength of steel, the structure of a snowflake, all of it is electromagnetism doing the patient work of construction. And yet here, at the center of the atom, that same constructive force becomes purely destructive, a relentless engine of repulsion trying to blow the nucleus to pieces. The same force is creator and destroyer, depending only on the scale at which you meet it. That should tell you something important about physics. There are no simply good or simply bad forces. There are only forces acting in particular circumstances, and the same rule that builds in one place tears down in another. The nucleus is the place where electromagnetism, the great builder, turns demolition contractor, and where some other force must step in to undo its work. So what is it? What could possibly be strong enough to overpower a force equivalent to holding a suitcase out at arm's length, multiplied across dozens of particles, all packed into a space smaller than the imagination can properly hold? The natural first guess, the guess almost everyone makes, is the most familiar force we know, the force that holds us to the ground, that keeps the moon circling the earth and the earth circling the sun, the force that, on the largest scales, shapes the entire cosmos. Surely, if anything is going to hold a nucleus together, it must be gravity. After all, gravity is an attractive force. It acts between anything that has mass, and protons most certainly have mass. So before we meet the real hero of this story, we owe gravity its moment in the spotlight. We need to ask, honestly and with the numbers in hand, whether gravity is the thing holding the nucleus together. And the answer is going to surprise you, because it is going to be one of the most lopsided defeats in all of physics. Part 3. The force that doesn't stand a chance. Let us give gravity a fair hearing. We will take the very same two protons, sitting at the very same separation of 1 femtometer, and this time, instead of calculating how hard they push apart electrically, we will calculate how hard they pull together gravitationally. For this we reach for one of the most famous equations ever written, Newton's law of universal gravitation. It tells us that the attractive force between two objects is proportional to the product of their masses and inversely proportional to the square of the distance between them. It is the same equation that describes the pull between the Earth and the Moon, between the Sun and the planets, between galaxies drifting across the void. It is universal. It applies to two protons just as faithfully as it applies to two stars. The mass of a single proton is tiny, about 1.67 times 10 to the minus 27 kilograms. That is a decimal point, followed by 26 zeros, and then the digits. We take that mass, and the same mass for the second proton, and the same 1 femtometer separation, and we feed it all into Newton's equation, and out comes the gravitational force of attraction between our two protons. It is roughly 1.87 times 10 to the minus 34 newtons. Sit with that number for a moment, because it is not just small. It is so small that the word small does not really do it justice. The electric repulsion we calculated was around 230 newtons. The gravitational attraction is around 1/10,000 billionth of a single newton. To compare them properly, we take the ratio of the two forces, dividing the electric repulsion by the gravitational attraction. And the answer that comes back is a number greater than 10 to the 36. That is a 1 followed by 36 zeros. I want you to really feel the size of that gap, because our intuition is hopeless with numbers this large. If you had a single grain of sand, and you wanted to gather 10 to the 36 grains, you would need vastly more sand than exists on every beach and in every desert on Earth. You would need more grains of sand than there are stars in the observable universe, many times over. That is the factor by which the electric force beats gravity inside the nucleus. Gravity does not merely lose this contest. It is not even in the same arena. It is not even playing the same sport. Asking gravity to hold a nucleus together against electric repulsion is like asking a single feather to hold back a landslide. It is the weakest force in the universe. And here, at the scale of two protons, it is being humiliated by a factor with 36 zeros. So gravity is out. Whatever holds the nucleus together It is emphatically, overwhelmingly not gravity. And I want you to remember this defeat, because it is going to come back. This is the moment in our story where gravity is laughed out of the room, dismissed as hopelessly, absurdly feeble. Keep that image in your mind. The weakest force in the universe, beaten by 36 orders of magnitude, told it has no part to play. Because by the end of this story, that very same force, without ever getting any stronger, is going to rise up and become the single most powerful and most decisive player of them all. It is going to take everything we are about to build and crush it into something that bends space-time itself. But it cannot do that yet. Not at this scale, not with so little mass to work with. For now, gravity sits in the corner, defeated. It is worth understanding just how unusual gravity's weakness really is, because it is one of the genuine unsolved puzzles of physics. Nature has 4 fundamental forces. There is the strong nuclear force, the powerful one we are about to properly meet, which is the strongest of them all. There is the electromagnetic force, the one driving our proton repulsion, which is about 100 times weaker than the strong force. There is the weak nuclear force, fainter still, which governs certain kinds of radioactive decay. And then, far below all of them, almost comically far below, there is gravity. The gap between gravity and the other 3 is not small. It is the single largest gap between any of the forces, and physicists genuinely do not know why gravity is so absurdly feeble compared to everything else. They have a name for the puzzle, the hierarchy problem, but a name is not an explanation. The weakness of gravity is one of the things about our universe that we can measure with exquisite precision and still cannot account for. And yet, here is the twist that the rest of this story depends on. Gravity's weakness is real, but it is not the whole truth about gravity. The other 3 forces, for all their strength, are limited in ways gravity is not. The strong force, as we will see, reaches only as far as the next particle over. The weak force is even shorter ranged. And the electromagnetic force, while it reaches across any distance, comes in 2 opposite kinds, positive and negative, that tend to cancel each other out in any large body. Gravity alone has no opposite, no cancellation, no limit on its range. It is the only one of the 4 forces that simply adds up, particle by particle, across any amount of matter, all the way to the scale of planets and stars and galaxies. So while gravity loses every contest at the scale of 2 particles, it is quietly the only force built to dominate at the largest scales of all. Keep that asymmetry in mind. The force that cannot win a fight between 2 protons is the same force that shapes the entire universe. We have not seen the last of it. We have barely seen the first of it, which means we are still looking for our answer. We have ruled out gravity. The electric force is the problem, not the solution, since it is the thing trying to tear the nucleus apart. So there must be a third player, a force we have not yet named, something powerful enough to reach into that cramped nuclear interior and overpower a repulsion equivalent to dozens of loaded suitcases, all at once, and bind the whole thing into something stable. Before we meet it, let us linger one more moment on that defeat, because the more completely you understand how badly gravity loses here, the more astonishing its eventual victory will feel. A factor of 10 to the 36 is a number so large it actively resists comprehension. So let us try one more way of holding it. Imagine you wanted to weaken the electric repulsion until it was as feeble as gravity. You would have to take those 2 protons and pull them apart until the electric force had dropped by a factor of 10 to the 36. Because the electric force falls off as the square of distance, you would have to separate them not by a femtometer, not by a meter, not by the width of a country, but by a distance so enormous it would dwarf the separation between galaxies. That is how far apart you would need to drag 2 protons before their electric repulsion sank to the level of the gravity they feel while practically touching. Gravity, at the nuclear scale, is not just the runner-up. It is so far behind that the gap is measured in the geometry of the cosmos itself. And yet, and this is the thread to hold all the way to the end, gravity has one move that none of the other forces possess. It cannot be turned off, and it cannot be cancelled. Electric charges come in positive and negative, and tend to balance out to nothing. The strong force, mighty as it is, switches off the moment particles are no longer touching, but every scrap of mass, everywhere, pulls on every other scrap of mass, always, forever, with no opposite and no shield. So while gravity is the weakest force in any single contest, it is also the most patient and the most relentless. It never stops accumulating. Give it enough mass to gather, and those countless feeble pulls, none of which matters on its own, add together into something that can crush light itself. That is the reversal waiting for us. The force losing by a factor measured in the size of the universe is the same force that will, before this story ends, become the most powerful thing in it. But not yet. For now, gravity waits, and we turn to the force that actually does the job inside the nucleus. There is such a force. It is one of the 4 fundamental forces of nature, and yet most people could not name it, because it never shows itself in the world of everyday experience. It hides entirely inside the nucleus, never reaching out into the larger world we can see and touch. It is called the strong nuclear force, and it is about to introduce us, at last, to the true purpose of the neutron. Because the strong force is the muscle that holds matter together, but it has a strange and crucial weakness, and it is that weakness, more than its strength, that will decide just how many neutrons we can ever hope to stack. Part 4. The perfect building block. The strong nuclear force is the most powerful of the 4 fundamental forces, and it is the answer to the riddle of the nucleus. It acts between all the particles we call nucleons, which is simply the collective name for protons and neutrons. It pulls proton to proton, proton to neutron, and neutron to neutron, binding them all together, and it is strong. At the scale of the nucleus, the strong force is roughly 100 times stronger than the electromagnetic force. So when 2 protons are trying to repel each other with the force of a suitcase held at arm's length, the strong force is there, pulling them back together with something like 100 times that strength. That is more than enough to win. That is how the nucleus survives the war we just described. The strong force overpowers the electric repulsion, and matter holds. But the strong force has a catch, and this catch is the single most important property in our entire story. Unlike gravity, and unlike electromagnetism, which reach out across enormous distances, growing weaker with separation but never truly stopping, the strong force has almost no reach at all. It is strictly short-ranged. It only operates between particles that are practically touching, immediate neighbours sitting right beside each other. Step even a little further away, and the strong force simply switches off. It does not weaken gradually the way gravity does over astronomical distances. It vanishes. A nucleon feels the powerful grip of the strong force only from the handful of other nucleons directly around it, and from no one else. To see why that matters so much, picture a large nucleus as a dense cluster of spheres, with the protons in red and the neutrons in blue, all packed together. Now focus your attention on a single proton, somewhere in the middle of that cluster. Because the strong force is short-ranged, this proton is gripped tightly only by the nucleons immediately surrounding it, the ones it is practically touching. Those near neighbours hold it firmly in place. Pick a different proton, anywhere in the nucleus, and the same is true. It too is bound only by its own immediate neighbours. The strong force, powerful as it is a strictly local affair. Every nucleon is held by its neighbours and is blind to everything beyond them. Now compare that with the electric repulsion and you will see the trap closing. The electric force is long-ranged. A proton on one side of the nucleus repels a proton on the far opposite side across the entire width of the cluster, even though they are nowhere near touching. So consider a single proton again. The strong force binding it is limited, coming only from its immediate neighbors. But the electric repulsion pushing it outward comes from every other proton in the entire nucleus, near and far, all of them adding their push. And here is the fatal asymmetry. As a nucleus grows larger, and you pack in more and more protons, the electric repulsion on each proton keeps climbing, because every new proton you add pushes on all the others. But the strong force binding each proton does not climb in the same way. It stays limited to a few neighbors, and can even weaken as the geometry crowds and the surface grows. The repulsion scales with the total number of protons. The binding does not. Eventually, inevitably, the repulsion catches up, and the balance tips toward instability. This is not a hypothetical. It is the reason the heaviest elements in the periodic table are radioactive. Elements like uranium, with their 92 protons, are sitting right at the edge of this cliff. The electric repulsion has grown so large that the strong force can barely hold the nucleus together, and so, every now and then, it does not. The nucleus spits out a fragment, or splits apart entirely, in the process we call radioactive decay. Large nuclei are not comfortably stable. They are balanced on a knife edge, perpetually close to falling apart. And this, at last, is where the neutron steps out of the shadows and reveals its genius. Remember that a neutron carries no electric charge. That means that no matter how many neutrons you add to a nucleus, they contribute absolutely nothing to the electric repulsion. They do not push on the protons, and they do not push on each other. But, crucially, they do feel the strong force, and they do contribute to it, binding to every nucleon around them. So a neutron is a remarkable thing. It adds to the glue holding the nucleus together, while adding nothing at all to the force trying to tear it apart. It is binding with no cost. It is, in the most literal sense, the perfect adhesive. This is why, as nuclei grow larger, they need more and more neutrons to survive. The growing army of protons brings a growing storm of repulsion, and the only way to counterbalance it without making the problem worse is to pack in extra neutrons, adding strong force binding while keeping the electric cost at zero. Without that growing surplus of neutrons, large atoms simply could not exist. They would tear themselves apart in an instant. Quietly, invisibly, with no charge and no drama, neutrons are the reason the heavy half of the periodic table exists at all. The iron in your blood, the calcium in your bones, the heavy elements that make up so much of the world, all of them are held together by neutrons silently absorbing a repulsion that would otherwise shatter them. You can actually watch this neutron arithmetic play out as you climb the periodic table, and it tells a quiet story of escalating need. In the lightest elements, the balance between protons and neutrons is roughly even. Ordinary carbon has 6 protons and 6 neutrons, a 1-to-1 match. Oxygen has 8 of each. At this end of the table, the proton repulsion is still modest, and a nucleus can get by with about as many neutrons as protons. But as you move to heavier elements, the ratio begins to tilt. By the time you reach iron, with 26 protons, the most stable form carries 30 neutrons, noticeably more neutrons than protons. Keep climbing. Gold, with 79 protons, needs around 118 neutrons. And uranium, near the very top, with 92 protons, requires about 146 neutrons just to hold together at all. The pattern is unmistakable. The more protons you pack in, the more the repulsion grows, and the more extra neutrons you must add to dilute that repulsion and supply enough strong force binding to survive. This is what physicists call the valley of stability, the narrow band of proton to neutron ratios where nuclei can actually exist without immediately falling apart. Stray too far from that band in either direction, too many neutrons or too few, and the nucleus becomes unstable and decays. And the valley has an end. Past uranium, even piling on extra neutrons is no longer enough to win the fight. The repulsion has simply grown too large for any ratio to contain, which is why there are no stable elements beyond a certain point, and why the heaviest elements we can make in laboratories survive for only fractions of a second before they come apart. So, neutrons are not just helpful. For everything heavier than the lightest few elements, they are the difference between existing and not existing. They are, quietly, the thing that lets the periodic table extend past hydrogen and helium into the full range of matter that builds worlds and living things. So now look at what we seem to have discovered. The neutron appears to be the ideal building block. No charge, no conflict, no repulsion to fight against. Just pure, cost-free binding through the strong force. And if that is true, then our innocent question seems to have an easy and thrilling answer. If neutrons add only binding and never repulsion, then surely we can just keep adding more. There is no electric storm to worry about, because neutrons do not create one. It begins to look as though there is no limit at all, that we could pile neutrons together endlessly and build an object of any size we please. The door to infinity seems wide open, and it is precisely at this moment, when the answer feels settled and the path forward looks clear, that quantum mechanics steps in and slams that door shut. Part 5. The door quantum mechanics slams shut. The trouble with the idea of endlessly stacking neutrons is that neutrons are not classical objects. They are quantum particles, and quantum particles live by rules that have no parallel in the everyday world. The particular rule that ruins our plan is one of the most profound and far-reaching principles in all of physics. To understand it, we first need to know what kind of particle a neutron is. Particles in the universe come in two broad families, and the difference between them shapes the structure of all matter. The neutron belongs to a family called fermions, named after the Italian physicist Enrico Fermi, who helped uncover the rules they obey. Protons are fermions too, and so are electrons. The defining feature of fermions is captured in a single, deceptively simple statement known as the Pauli exclusion principle. It says that no two identical fermions can ever occupy the same quantum state at the same time. Each one must have its own distinct state. They cannot pile up together into a single, shared condition. They are, in a sense, intensely private particles, and the universe enforces that privacy absolutely. When we apply this principle to a collection of neutrons, the consequence is immediate and severe. The neutrons cannot all settle down into the lowest, most comfortable energy level together. The exclusion principle forbids it. Instead, they are forced to stack themselves into a ladder of distinct energy levels, filling them from the bottom up. You can fit two neutrons into the very lowest level, one spinning one way and one spinning the other, because that tiny difference in spin makes their quantum states distinct, but that is all the lowest level will hold. The next two neutrons are forbidden from joining them and must climb to the next level up. The next pair climbs higher still, and the next pair higher than that. Let me give you a picture for this, because it makes the strange rule feel almost familiar. Imagine a tall hotel, and imagine that the guests arriving are your neutrons. The hotel has a peculiar policy. Each floor can hold only 2 guests, and every guest must take the lowest available floor. The first 2 guests arrive and take the ground floor. The next 2 are turned away from the ground floor, which is now full, and sent up to the first floor. The next 2 go up to the second floor, and so on. As more and more guests arrive, the lower floors fill completely, and every newcomer is forced higher and higher up the building. The guest who arrives late does not get to rest comfortably on the ground floor. They are sent climbing far up into the tower to whatever empty room remains at the top. Now here is what that climbing actually means for our neutrons. In this quantum hotel, the higher floors are not just higher up, they are higher in energy. A neutron forced into a high energy level is a neutron carrying a great deal of energy, moving fast, restless, and barely contained. As you keep adding neutrons to your growing pile, the lower energy levels fill, and each new neutron is forced to occupy a level higher in energy than the last. The average energy of the neutrons keeps climbing relentlessly with every one you add, and this cannot go on forever. There is a ceiling, and it is set by the strong force itself. The strong force can only hold a neutron in place with a certain amount of binding energy. It is strong, but it is not infinite. So as you stack more and more neutrons, and their energies climb higher and higher up that quantum ladder, you eventually reach a point where the topmost neutrons are carrying more energy than the strong force can contain. Picture that late arriving hotel guest sent so far up the tower, so high in energy, that the building can no longer hold them. At that point, the neutron is no longer bound. It simply leaves. It escapes the pile entirely. Once the energy of the added neutrons exceeds the binding energy holding them in place, the strong force loses its grip, and the neutrons begin to boil away, flying off into the surroundings faster than you can add new ones. To feel how strange this rule is, imagine for a moment a universe where it did not apply. There is, in fact, another whole family of particles, called bosons, that do not obey the exclusion principle at all. Bosons are perfectly happy to pile into the same quantum state, as many as you like, all sharing the lowest energy level together. Particles of light, photons, are bosons, which is part of why you can make a laser, a beam of countless light particles, all marching in the same identical state. Now imagine if neutrons behaved that way, if they were bosons instead of fermions. Then our entire problem would vanish. You could pour neutron after neutron into the lowest energy level, with no rising ladder of energy, no escalating pressure, no boiling off. They would simply settle together at the bottom, and there would be no quantum wall at all. The fact that we cannot do this, the fact that neutrons stubbornly refuse to share, is not a minor detail of bookkeeping. It is the entire reason matter resists being compressed, the reason there is a limit to stacking at all. The exclusion principle is the source of the wall, and the wall exists only because neutrons happen to belong to the family that insists on privacy rather than the family that loves a crowd. It is worth pausing on how profound and how universal this principle really is, because the Pauli exclusion principle is not some obscure technicality. It is one of the load-bearing pillars of reality, the reason the world has structure at all. Consider that the same rule applies to electrons. Electrons are fermions too, and the exclusion principle is precisely why they arrange themselves into distinct shells around an atom, rather than all collapsing into the lowest energy level together. That shell structure is the entire basis of chemistry. It is why different elements have different properties, why some atoms bond eagerly and others not at all, why the periodic table has the shape it does. If electrons could pile into the same state freely, every atom would behave almost identically, chemistry would not exist, and neither would you. The exclusion principle is the rule that gives matter its variety and its solidity. When you press your hand against a table, and it does not pass through, part of what you are feeling is electrons refusing, by this very principle, to be pushed into states already occupied. And this same refusal, this insistence on privacy, is what governs our neutrons. There is also a startling parallel that we will return to later. The exclusion principle, acting on electrons, produces a quantum pressure of its own, and that pressure is what holds up a different kind of stellar corpse, a white dwarf against gravity. White dwarfs are stars supported not by heat or fusion, but purely by the unwillingness of their electrons to share quantum states. So the very same principle that is about to cap our neutron pile is, elsewhere in the universe, already busy holding up the dead cores of stars. It appears again and again, in matter at every scale, an invisible rule that quietly shapes atoms, chemistry, and the corpses of stars alike. And right now, for us, it is the wall. It is the reason our beautiful plan to stack neutrons without limit is about to fail. And so quantum mechanics, all on its own, with no help from gravity or electromagnetism, builds a hard ceiling into our plan. You cannot just keep adding more neutrons. The Pauli exclusion principle forces each new one to a higher energy, and beyond a certain point, they will not stay. The perfect building block has betrayed us. The very feature that made it seem limitless, the absence of electric repulsion, does nothing to save it, because the limit comes not from any force at all, but from a fundamental counting rule about quantum states. The door that looked wide open to infinity has been quietly, firmly shut. So now we have hit two separate walls. Add too many protons, and electric repulsion blows the nucleus apart. Add too many neutrons, and the exclusion principle drives their energy so high that they escape. Either way, the universe says no. We seem to be completely stuck. And yet, the most extraordinary part of this story has not even begun, because there is a third option we have not yet tried, and it involves waking up the very force we left defeated in the corner. Part 6. Trapped between two failures. Let us take stock of exactly where we stand, because the trap we are in is the doorway to everything that follows. We set out to build an object from particles, just stacking more and more, and we have discovered that nature blocks the path in two different ways. On one side, if we try to build with charged particles, with protons, the long-ranged electric repulsion grows without mercy as the structure gets bigger until it overwhelms the short-range strong force and the whole thing flies apart. That is the lesson of radioactivity, the reason there are no stable elements far beyond uranium. On the other side, if we try to escape that problem by building with neutral particles, with neutrons, we run headlong into the Pauli exclusion principle, which forces each new neutron to a higher energy until they carry more than the strong force can hold, and they boil away into the dark. Too many protons, and repulsion wins. Too many neutrons, and quantum mechanics wins. Both roads end at a wall. It would be easy to conclude, here, that the answer to our question is simply a modest number, that you can stack neutrons only up to some limit set by the strong force and the exclusion principle, a pile no bigger than a large nucleus, and that is the end of the story. And if the strong force were the only thing capable of binding matter together, that conclusion would be correct. But it is not the only thing. There is another force in this story, one we have not asked to do any real work yet, one we dismissed many minutes ago as utterly hopeless. And it is time to wonder whether we gave up on it too soon. And yet there is a quiet clue sitting in plain sight, one we passed over earlier without remarking on it. When we calculated the gravity between two protons and found it hopelessly weak, we treated gravity as a single, fixed thing, weak and irrelevant. But gravity is not fixed. Its strength in any situation depends entirely on how much mass is gathered and how closely it is packed. We dismissed gravity because we were only ever looking at two particles at a time. We never asked what gravity would do if we stopped thinking about pairs and started thinking about staggering numbers of neutrons all at once. That was the unexamined assumption in our defeat. We assumed gravity was weak because it is weak between two things, and we never tested whether it stays weak between a trillion things. This is the kind of hidden assumption that, once you notice it, cracks a problem wide open. The weakness of gravity was never a property of gravity itself. It was a property of how little mass we had given it to work with. Think back to the contest between the electric force and gravity when we placed two protons 1 femtometer apart. Gravity lost by a factor of more than 10 to the 36, a defeat so total that we laughed it out of the room. But pause and ask why gravity lost so badly. It was not because gravity is weak in some absolute, unchangeable sense. It lost because we were dealing with only two particles, two tiny masses, and gravity between two tiny masses is genuinely negligible. But gravity has a property that no other force in this story shares, a property that changes everything once the numbers get large enough. Gravity always attracts, and it never cancels out. This is the secret that is about to turn the whole story on its head. The electric force comes in two flavors, positive and negative, attraction and repulsion, and those flavors cancel. Put a positive charge next to a negative one, and from a distance their effects largely erase each other. That is why bulk matter, made of equal parts positive protons and negative electrons, is electrically neutral overall and exerts almost no electric force on distant objects. The electric force, for all its ferocity up close, tends to neutralize itself in large collections of matter. But gravity has no negative version. There is no such thing as negative mass cancelling positive mass. Every particle with mass attracts every other particle with mass, always, with no cancellation and no shielding. Which means that while the electric force tends to cancel itself away as objects grow larger, gravity does the opposite. It accumulates. Every additional particle you add throws its own small pull onto the total, and the total only ever grows. So here is the new idea, the pivot on which the rest of this story turns. What if we stop relying on the strong force to hold our neutrons together at all? What if, instead of fighting the quantum ceiling, we simply pack so many neutrons into one place, at the crushing densities found inside a nucleus, that their combined mass finally makes gravity matter? Individually, the gravity of a neutron is nothing, a number with 34 zeros after the decimal point. But gravity accumulates. Gather enough neutrons, and all of those negligible little pulls add up and add up and add up, until the total is no longer negligible at all. Until, perhaps, gravity becomes strong enough to hold the entire pile together by itself, with no help from the strong force whatsoever. To feel why accumulation changes everything, think about what happens as you gather more and more matter into one place. Take two neutrons, and the gravity between them is a number so small it barely deserves to be written down. Add a third, and now each neutron is pulled by two others. Add 1,000, and each one feels the combined pull of 999 neighbors. Add 1,000,000,000,000,000, and the pull on any single neutron is the summed gravity of every other neutron in the entire pile, all of it pointing inward, none of it cancelling. The force per particle keeps climbing as the pile grows, because gravity has no off switch and no opposite. This is the property that makes stars and planets possible in the first place. A single atom's gravity is nothing, but the Earth, which is just an enormous number of atoms gathered together, pulls on you hard enough to hold you to its surface and hard enough to keep the moon circling it for billions of years. The gravity you feel right now, pinning you to your seat, is nothing more than the accumulated, never-cancelling pull of roughly 10 to the 50th atoms beneath you. So the question we are really asking is one of accumulation. How much neutron matter must we gather before the summed gravity of the whole pile becomes strong enough to trap even those restless, high-energy neutrons that the exclusion principle keeps trying to fling away? We are no longer pitting gravity against electromagnetism between two particles, the contest gravity lost so badly. We are giving gravity the one thing it was always waiting for, which is sheer quantity, an enormous heap of mass for its tiny, relentless, never-cancelling pulls to add up across. And the astonishing thing, The thing that should make you sit up is that the amount of mass required is not some impossible cosmic quantity beyond all reckoning. It is a definite, calculable number. We can work it out. And to work it out, we do not need a supercomputer or the full apparatus of Einstein's relativity. We need a single, beautifully simple argument and some mathematics no harder than what you learned in school. It sounds almost absurd given how badly gravity was beaten just a few minutes ago. But the question is no longer whether gravity can compete with the electric force between two protons. The question is how much mass we would need to gather at nuclear density before gravity alone becomes strong enough to trap even the restless, high-energy neutrons that the exclusion principle keeps trying to fling away. In other words, we are no longer asking whether we can build an object out of neutrons. We are asking how big that object would have to be before gravity takes over the job of holding it together. And the moment gravity takes over, the moment it becomes the thing binding the neutrons in place, our humble pile of particles stops being a pile at all. It becomes something else entirely. It becomes one of the most extreme objects in the universe. To find out how massive it must be, we are going to do something that sounds impossible. We are going to weigh a star using nothing but high school mathematics. Part 7. The weakest force takes its revenge. To find out how much mass we need before gravity takes command, we are going to follow a beautifully simple line of reasoning, a back-of-the-envelope argument due to the physicist Bernard Schutz, laid out in his book Gravity from the Ground Up. What makes this argument so wonderful is that it uses nothing more than high school mathematics, and yet it lands astonishingly close to what the full machinery of general relativity predicts. It is one of the clearest demonstrations you will ever see of how far a little physical intuition can carry you. So let us walk through it together, slowly, one step at a time. We begin with a fact that has been measured in laboratories countless times and is rock solid. In a typical atomic nucleus, it takes about 8 mega-electron volts of energy to remove a single nucleon, whether a proton or a neutron, from the nucleus. That is the average binding energy per nucleon, the energy you would have to supply to pry one particle loose from the grip of the strong force. 8 mega-electron volts. Hold on to that figure, because it is the key that unlocks everything. Now comes the clever step. We are going to take that binding energy, the energy needed to remove a nucleon, and we are going to convert it into a speed. Specifically, we ask, how fast would a neutron have to be moving in order to carry exactly that much energy as energy of motion? We do this using the most basic equation for kinetic energy, the one every physics student learns, which says that kinetic energy equals 1/2 the mass times the velocity squared. We set that kinetic energy equal to the binding energy, 8 mega-electron volts, and then we rearrange to solve for the velocity. The velocity comes out as the square root of 2 times the energy divided by the mass. Let us put the numbers in. 8 mega-electron volts, converted into standard units, is about 1.28 times 10 to the minus 12 joules. The mass of a neutron is about 1.67 times 10 to the minus 27 kilograms. We divide, we double, we take the square root, and out comes a velocity. The number is 3.92 times 10 to the 7 meters per second. To make sense of that, compare it to the speed of light, which is about 3 times 10 to the 8 meters per second. Our neutron would need to travel at over 10% of the speed of light to carry enough energy to escape a nucleus. That is the escape velocity we are aiming for. If we want gravity to trap our neutrons, gravity must be strong enough to hold back a particle trying to flee at more than 1/10 the speed of light. So now we flip the question around and point it at gravity. How massive would a ball of neutrons packed at nuclear density have to be so that its own gravitational escape velocity reaches that same value, 3.92 times 10 to the 7 meters per second. For any spherical object, there is a well-known formula for the escape velocity at its surface, the speed something needs to break free of its gravity entirely. That escape velocity is the square root of 2 times Newton's gravitational constant times the mass divided by the radius. The more mass, the higher the escape velocity. The larger the radius, the lower it. Now, because we are insisting that our ball is made of neutrons packed at nuclear density, the mass and the radius are not independent. They are tied together because density is just mass divided by volume, and the volume of a sphere is 4/3 times pi times the radius cubed. Hold the density fixed at the nuclear value, and the radius is locked to the mass. Bigger mass means bigger radius, in a fixed proportion. When we take that relationship between mass and radius and substitute it into the escape velocity formula, something elegant happens. After the algebra settles, we find that for an object of constant density, the escape velocity scales with the mass raised to the 1/3 power. The more massive the object, the higher its surface escape velocity, growing steadily as the cube root of the mass. That makes perfect physical sense. Pile on more mass at fixed density, and the gravity at the surface gets stronger, and it gets harder to escape. Now we simply demand that this escape velocity equal the value we need, 3.9, 2 times 10 to the 7 meters per second, and we solve for the mass. We plug in the nuclear density and Newton's constant, and we turn the crank. The answer that emerges is a mass of about 3.9 times 10 to the 28 kilograms. On its own, that number means little, so let us compare it to something familiar. The mass of our Sun is about 2 times 10 to the 30 kilograms. Our result is roughly 2% of the mass of the Sun. So there it is, our first real answer. If you could gather neutrons at nuclear density into a ball weighing about 2% of the Sun, then gravity, all by itself, would be strong enough to hold even the most energetic surface neutrons from escaping. Below that mass, the high-energy neutrons could still fling themselves free. At or above it, gravity traps them. And an object held together this way is no longer a nucleus. It is no longer relying on the strong force at all. It is bound by gravity. It has become, by definition, a neutron star. Let us make sure that escape velocity idea is solid, because it is doing a lot of work here. Escape velocity is simply the speed at which something must move to break free of an object's gravity forever, never to fall back. On Earth, the escape velocity is about 11 kilometers per second. Throw a ball slower than that, and it comes back down. Launch a rocket faster than that, and it can leave the planet entirely and never return. The more massive and the more compact an object is, the higher its escape velocity, because its surface gravity is stronger. The clever move in this whole argument is to recognize that escaping a nucleus and escaping a gravitating ball are, mathematically, the same kind of problem. In both cases, we ask how much speed a particle needs to break free. So we measured the speed a neutron needs to flee a nucleus, just over 1/10 of the speed of light, and then we asked what it would take for gravity, all by itself, to demand that same speed. If gravity's escape velocity matches the nuclear one, then gravity is pulling exactly as hard as the strong force was, and it can take over the job of holding the neutrons in. And the number that fell out, 3.92 times 10 to the 7 meters per second, is genuinely arresting when you sit with it. We are talking about an escape velocity of over 30,000 kilometers every second. Light itself travels at about 300,000 kilometers per second, so we are asking gravity to hold back particles that would otherwise flee at more than 10% of the speed of light. There is nothing on Earth that comes remotely close. The fastest spacecraft humans have ever built crawl along at a tiny fraction of that. To trap something moving at 1/10 of light speed, you need a gravitational pull of a ferocity that exists nowhere in ordinary experience, a pull that only appears when you crush a star's worth of matter into a ball at nuclear density. That is the threshold we just located with nothing but a kinetic energy formula and a number from a textbook, and it points directly at how much mass we must gather for gravity to reach that ferocity. Stop and feel the weight of what just happened, because this is the turning point of the entire story. Remember gravity in the corner of the room. Remember the weakest force in the universe, beaten by a factor of more than 10 to the 36, dismissed and humiliated when we had only 2 protons to work with. It never got any stronger, not for a moment. The force itself did not change at all. All that changed was the amount of mass we gathered together. And because gravity never cancels, because every single neutron threw its tiny pull onto the pile and none of it ever erased, those negligible little tugs accumulated and accumulated until the force we laughed out of the room rose up and seized control of the whole structure. The weakest force in the universe, given enough to work with, becomes the strongest hand on the table. That is gravity's revenge, and we are only beginning to see what it can do. Part 8. Weighing a Star with High School Math. Our first estimate was good, but it was, if you look closely, a little crude. It asked only one narrow question. Can a single neutron, sitting right at the surface, at the very edge of the ball, escape? It was a surface criterion, a local check on the outermost particles. But a neutron star is not held together merely by clinging to its surface. It is stable because every neutron throughout its entire volume is bound by the collective pull of all the others. So to do better, we need to ask a deeper, more complete question. Not whether one edge particle can escape, but how much energy it would take to pull the entire object apart, piece by piece, against its own gravity. That total is called the gravitational binding energy, and using it gives us a more honest estimate. The gravitational binding energy of a uniform sphere is the total energy you would have to supply to disassemble it completely, lifting away every shell of material against the gravity of everything beneath it until nothing is left. For a sphere of constant density, this energy works out to 3/5 times Newton's gravitational constant times the mass squared, divided by the radius. That factor of 3/5 is not a fudge or a guess. It falls out cleanly when you add up the gravitational energy of every concentric shell that makes up the sphere using a bit of calculus. It is exact for a uniform ball. Now we play the same trick as before. We use the fact that our object is made of neutrons at nuclear density to relate its radius to its mass, and we substitute that relationship into the binding energy formula. After the dust settles, we have an expression for the total gravitational binding energy of our neutron ball purely in terms of its mass and the fixed nuclear density. This tells us how much energy gravity is using to hold the whole thing together. And here is the decisive comparison. We take that gravitational binding energy and we set it equal to the total nuclear binding energy that the strong force would have provided for the same amount of material. We know each nucleon is bound by about 8 mega-electron volts. So the total strong force binding is simply the number of neutrons multiplied by 8 mega-electron volts each. And the number of neutrons is just the total mass of the object divided by the mass of a single neutron. When the gravitational binding energy grows large enough to equal the total binding the strong force could have supplied, gravity has genuinely taken over the job. At that mass, gravity is doing as much work holding the object together as the strong force ever could. And beyond it, gravity is firmly in charge. So we set the two binding energies equal, and we solve for the mass. After a little rearranging, out comes a new estimate. About 8.5 times 10 to the 28 kilograms. Compared to the Sun, that is roughly 4.3% of a solar mass, more than twice our first estimate. And that increase makes complete sense. This calculation accounts for the energy needed to unbind the entire object, every neutron in it, not just whether a single particle at the surface can slip away. It is a more global, more complete picture, and so it gives a larger and more trustworthy minimum mass. But notice that everything we have done so far, both estimates, has used nothing but Newtonian physics, the physics of Newton's gravity and basic mechanics. And while it has carried us remarkably far, it is not the final word, because inside a real neutron star, gravity becomes so intense that Newton's description begins to break down. We need Einstein. In the extreme conditions inside such an object, gravity is so strong that even pressure, the outward push of the matter itself, contributes to the gravitational field and makes gravity stronger still. Space-time curves inward upon itself, amplifying the pull in ways Newton never imagined. These effects are captured by a set of equations known as the Tolman-Oppenheimer-Volkoff equations, named after the physicists who derived them. They are the relativistic version of the balance between pressure pushing out and gravity pulling in, and they describe how pressure, mass, and density change as you move through the interior of a spherical star. Solving them with a realistic description of how nuclear matter behaves gives the true minimum mass for a stable neutron star, and that true value comes out to about 1/10 of the mass of the Sun. That idea, that pressure itself can become a source of gravity, deserves a moment, because it is one of the strangest features of Einstein's universe, and it has no parallel in everyday physics. In Newton's world, only mass creates gravity. The heavier something is, the more it pulls. But Einstein revealed that gravity responds not just to mass, but to energy in all its forms, and to pressure as well. Inside a neutron star, the matter is under such monstrous pressure, pushing outward to resist the crush, that the pressure itself adds to the gravitational field. Think about how perverse that is. The outward pressure is the very thing trying to hold the star up against gravity, and yet that same pressure, by Einstein's rules, makes the gravity stronger. The harder the matter pushes back to save itself, the heavier it effectively becomes, and the deeper the hole it digs. This is a feedback that simply does not exist in Newtonian physics, and it is one of the reasons a neutron star sits on such a knife edge. Past a certain point, pushing back harder no longer helps, it hurts. The defense feeds the attacker. This is exactly the effect the Tolman-Oppenheimer-Volkoff equations capture, and it is why we cannot get the truly correct answer from Newton alone. Those equations describe, layer by layer, how the pressure must change as you move from the surface of the star down toward its center, balancing the inward crush of gravity against the outward push of the matter, all while accounting for the fact that pressure and energy are themselves feeding the gravity. They are not simple equations, and in general they must be solved with computers, fed with a description of how nuclear matter behaves when it is squeezed beyond anything we can reproduce on Earth. But when you do solve them, they reward you with the genuine minimum mass for a stable neutron star, the real floor below which gravity cannot bind such an object. And that floor sits at about 1/10 of the mass of our Sun, only modestly above the cruder Newtonian estimates we reached with pencil and paper. Look at how close our crude estimates came. The full relativistic answer is about 0.1 solar masses. Our simple back-of-the-envelope arguments gave about 0.02 and about 0.043 solar masses. We landed within a factor of 2 or so of the real answer, using nothing but high school mathematics. And consider the span we just crossed. We started with the mass of a single neutron, around 10 to the minus 27 kilograms, and we reasoned our way up to the mass of a neutron star, around 10 to the 28 kilograms. That is a leap of more than 55 orders of magnitude, 55 factors of 10, from one of the smallest objects in nature to one of the most extreme, and our simple tools held up the entire way. There is something quietly astonishing in that. It tells you that the universe, for all its strangeness, is genuinely comprehensible, and comprehensible with tools so modest that a curious teenager with a pencil could wield them. We have found the floor, the minimum mass below which a ball of neutrons cannot hold itself together. But every floor has a ceiling above it. And the ceiling, it turns out, is where gravity stops being our ally and becomes something far more frightening. Part 9. The other edge of the cliff. We have found the minimum mass. Gather less than about 1/10 of the sun's mass in neutrons, and gravity is too weak to bind them, and the structure cannot form. But what about the other direction? What is the most massive a neutron star can be? Is there a ceiling, a point beyond which adding more neutrons stops building something stable and starts building a catastrophe? There is, and to understand it we have to return to an old acquaintance, the very principle that first blocked our path. The Pauli exclusion principle is about to switch sides. Recall that neutrons are fermions, and that no two of them can occupy the same quantum state. When we were stacking neutrons in a nucleus, this principle worked against us, forcing them to higher and higher energies until they boiled away. But inside a neutron star, that same principle becomes the hero. As gravity crushes the neutrons together, trying to squeeze them into the same states, the exclusion principle resists. It absolutely forbids the neutrons from being pushed into identical conditions, and that refusal generates an enormous outward pressure. We call it neutron degeneracy pressure, and it has nothing to do with temperature or motion in the ordinary sense. It is a pure quantum pressure, arising entirely from the neutron's stubborn refusal to share quantum states. It is this degeneracy pressure that holds a neutron star up, bracing it against the relentless inward crush of its own gravity. The very principle that once kept us from stacking neutrons is now the only thing keeping the star from collapsing. But, and this is the crucial point, neutron degeneracy pressure has a limit. It is strong, but it is not infinite. As we add more and more mass to the neutron star, gravity grows stronger and stronger, pressing inward with ever greater force. For a long while, the degeneracy pressure can match it, pushing back hard enough to hold the structure in balance. But there comes a point where gravity simply becomes too strong. The inward pull grows so immense that not even the quantum refusal of the neutrons can withstand it. The degeneracy pressure, which has held the line through everything, finally gives way, and when it does, there is nothing left to stop the collapse. No known force in the universe can hold the matter up. The star can no longer support itself, and it falls inward without end, crushing down through every limit until it forms a black hole. This tipping point, the maximum mass a neutron star can have before gravity overwhelms even degeneracy pressure, is called the Tolman-Oppenheimer-Volkoff limit, after the same physicists whose equations gave us the minimum. When general relativity is properly accounted for, this maximum mass is estimated to lie somewhere between about 2.2 and 2.9 times the mass of the Sun. The exact value depends on details we do not fully understand, the precise behavior of matter at densities beyond anything we can reproduce on Earth, which is why it is quoted as a range rather than a single number. But the message is clear. Somewhere between roughly 2 and 3 solar masses, the neutron star reaches its absolute ceiling. Pile on more than that, and no stable configuration exists. Gravity finishes what it started, and the object disappears behind the one-way door of a black hole. The reason that maximum mass is quoted as a range, rather than a single sharp number, is itself one of the most fascinating open questions in physics, and it comes down to a simple admission. We do not actually know what the center of a neutron star is made of. Near the surface, we are fairly confident it is neutrons packed together. But as you descend toward the core, the pressure climbs to values beyond anything we can create or test in any laboratory, and at those pressures, the neutrons themselves may stop being the fundamental building blocks. They may be crushed so hard that they dissolve, breaking apart into the even smaller particles they are made of, the quarks, which would then roam freely in a state sometimes called quark matter or strange matter. Or the core might fill with exotic heavy particles called hyperons, cousins of the neutron that carry a property called strangeness. Or it might form a strange quantum condensate of yet other particles. Each of these possibilities would make the matter respond to pressure slightly differently, which would shift the exact mass at which the star finally collapses. We are, in effect, uncertain about the maximum mass because we are uncertain about the deepest nature of the densest matter in existence. And this uncertainty is not a sign of failure. It is an active, living frontier of science. There even appears to be a curious gap in nature between the heaviest neutron stars, a little above 2 solar masses, and the lightest black holes, around 5 solar masses, a stretch of masses where, for a long time, almost nothing was observed. Whether that gap is real, telling us something profound about how collapse works, or whether it is just an artifact of how few objects we have measured, is something astronomers are still working out. And now we have a genuinely new way to probe it. When 2 of these compact objects spiral into each other and merge, they shake the fabric of space-time itself, sending out ripples we call gravitational waves, which our detectors on Earth can now catch. Sometimes those mergers involve an object whose mass falls right in the uncertain zone, leaving astronomers unable to say for certain whether they have just witnessed the heaviest possible neutron star or the lightest possible black hole. We are, for the first time, listening to the very boundary we calculated, the exact edge where neutrons give way to a black hole. It is worth appreciating just how unusual neutron degeneracy pressure is as a way of holding up a star, because it is nothing like what holds up the sun. Our sun, and every ordinary star, is held up against its own gravity by heat. The fusion in its core makes the gas hot, and hot gas pushes outward, balancing the inward pull. Take away the heat, let the fusion stop, and an ordinary star would simply deflate. But neutron degeneracy pressure is completely different. It does not depend on heat at all. It would hold the star up just as firmly at a temperature of absolute zero. It arises purely from the quantum refusal of the neutrons to share states, a pressure that exists even in cold, dead matter. This is why a neutron star can be a true stellar corpse, a thing with no fuel left to burn, and still stand against gravity for an effectively endless span of time. It is not a fire holding back the dark. It is a quantum principle, frozen in place, refusing to yield. And this gives us a clean way to see the whole architecture of these dying stars. There is a famous threshold, the Chandrasekhar limit, at about 1.4 solar masses, that marks where one kind of quantum pressure fails. Below it, the pressure of electrons refusing to share states can hold up a stellar corpse, and we call that corpse a white dwarf. Above it, electron pressure breaks, the star collapses further, and only the far stronger neutron pressure can catch it, producing a neutron star. And, above the higher limit we have just discussed, between about 2.2 and 2.9 solar masses, even neutron pressure fails, and nothing is left to catch the fall. So the universe builds its dead stars in a tier of escalating defenses, each quantum pressure stronger than the last, each with its own breaking point, and a black hole is simply what happens when the final defense gives way. A neutron star is the second to last stand against total collapse, the densest thing that still manages to hold itself up. So now we have both edges of the cliff, and they define something remarkable. There is a floor at about 1/10 of a solar mass, below which a ball of neutrons cannot hold together at all and would simply disperse. And there is a ceiling at somewhere between about 2.2 and 2.9 solar masses, above which the structure collapses into a black hole. A neutron star can only exist in the narrow band between these two limits. And this is the real answer to the question we have been chasing from the very beginning. How many neutrons can you stack before reality collapses? The honest answer is not a single number. It is a window. A range of masses, bounded below by gravity being too weak to bind, and bounded above by gravity being so strong that nothing can resist it. Below the window, your pile evaporates. Above it, your pile becomes a black hole. Only inside that window does something stable and extraordinary exist. Remember that phrase, a window, not a number, because it is going to matter more than you can yet imagine. We have spent all this time deriving these limits with mathematics, treating the neutron star as a theoretical possibility. But neutron stars are not theoretical at all. They are real. They are out there, scattered across the galaxy in their thousands. And what they are actually like, when you finally meet one, defies every instinct your mind possesses. Part 10. A star the size of a city. Neutron stars are not figments of theory or lines on a chalkboard. We have found them, studied them, timed their signals to the millionth of a second, and counted them across the sky. And when we tally up the masses of the ones we have measured, a clear pattern appears. The great majority of neutron stars have masses between about 1.2 and 2.1 times the mass of the Sun, and they cluster tightly around an average of roughly 1.4 solar masses. That number, 1.4, is not a coincidence, and later we will see exactly why nature keeps producing neutron stars right around that weight. But for now, let us take that typical neutron star, 1.4 times the mass of our Sun, and ask the simplest possible question about it. How big is it? If it weighs as much as a star, surely it must be enormous. We can estimate its size using the very relationship between mass and density we have been leaning on all along. We take that 1.4 solar masses, we assume it is packed at nuclear density, somewhere between 2 and 3 times 10 to the 17 kilograms per cubic meter, and we work out the radius of the sphere that would hold it. The answer comes back at somewhere between about 13 and 15 kilometers. Real neutron stars are not quite uniform. Their cores far denser than their outer layers, and when we feed them through the full machinery of general relativity, the predicted radius shrinks slightly to between about 11 and 13 kilometers. But our simple estimate, once again, lands remarkably close to the truth. Most people, hearing that a neutron star weighs as much as the Sun, instinctively imagine something huge. The Sun, after all, is enormous, more than 100 times the diameter of the Earth, so surely a thing as heavy as the Sun must also be immense. That instinct is exactly backward, and the reason why is the engine of this entire story. Gravity has not just gathered this matter together. It has crushed it, squeezed it past every barrier that normally gives matter its size, removed the empty space from inside the atoms, and packed the bare neutrons together until they touch. The result is not large at all. It is tiny. All of that mass, an entire star's worth, has been compressed into the smallest space that the laws of physics will still permit it to occupy without collapsing into a black hole. So a neutron star is the strange marriage of two extremes that never go together in ordinary life. The mass of a star and the size of a city fused into a single object. Heaviness and smallness, which our intuition insists are opposites, here become the same thing. Now stop and absorb what that means, because it is one of the most staggering facts in all of astronomy. We have an object more massive than the Sun, a thing that outweighs our entire star, and it is squeezed into a sphere no more than about 13 kilometers across. That is the width of a single city. To make it concrete, that is roughly the length of the island of Manhattan in New York. Imagine standing at one end of that island and looking down its length, and understanding that an entire star, something heavier than the Sun, has been crushed into a ball that would fit within your view. An object more massive than 450,000 Earths compressed into a space no wider than a city you could walk across in an afternoon. And to really feel how absurd that is, you have to zoom out, step by step. Manhattan is just a dot on a map of the United States. The United States is just a patch on the surface of the Earth. The Earth itself is a mere speck beside the enormity of the Sun, so small that more than 1 million Earths could fit inside our star. And yet, this tiny neutron star, no wider than a single city, no bigger than a dot on a speck, outweighs that entire Sun. The density required to do that is something the human mind was simply never built to hold. Let me try to give it to you anyway. Imagine you could reach down to the surface of a neutron star and scoop out a single teaspoon of its material. Just a teaspoon, the kind you stir into a cup of tea. That teaspoon of neutron star matter would have a mass of about 1.4 trillion kilograms. 1 teaspoon. That is more than the weight of a mountain. It is roughly the mass of every car in a large country, all of it balanced on a single spoon. There is nothing in your experience, nothing you have ever lifted or touched or imagined, that prepares you for matter this dense. Hold that teaspoon in your mind, weighing as much as a mountain range, and understand that this is not science fiction. It is simply what happens when gravity wins. Let me hold you on that teaspoon a little longer, because it is the single image in this whole story most worth sitting with. A teaspoon is a small, ordinary, domestic thing. You have held 1,000 of them, and the idea that one could weigh as much as a mountain is not slightly counterintuitive, the way some physics facts are. It is a complete overturning of everything your body knows about matter. When you lift a spoon, your muscles have built up a lifetime of expectation about how much a small object can weigh. That expectation is so deeply wired that you do not even notice it. A teaspoon of neutron star matter would tear straight through that expectation, through the spoon, through your hand, through the floor, through the earth, because nothing in ordinary experience is built to hold 1.5 trillion kilograms in the palm of a hand. And the reason it is so dense is not that the material is made of something heavy. It is made of the same neutrons that sit inside every atom of your body. The difference is only that gravity has squeezed out all the empty space, all that 99.999% of nothing that fills an ordinary atom, and packed the neutrons together until they touch. A neutron star is, in a sense, what matter looks like with the emptiness removed. It is your own atoms, the same particles you are made of, crushed down to their true, naked density. That is what should unsettle you. This is not alien material. It is ordinary matter, finally showing you how little of it there really is, and how much of what you call solid is simply space. And once you understand that a city-sized sphere can outweigh the sun, the rest of the numbers stop sounding like exaggerations and start sounding like consequences. The consequences of that density are violent in every direction. The escape velocity from the surface of a typical neutron star, the speed you would need to break free of its gravity, is about 1.67 times 10 to the 8 meters per second. That is more than half the speed of light. To leave the surface of this city-sized object, you would have to be moving at over 50% of the fastest speed anything in the universe can travel. A satellite skimming just above the surface, held in orbit by that ferocious gravity, would race around the entire star at about 1.18 times 10 to the 8 meters per second, completing a full orbit in roughly 0.71 milliseconds. Less than 1,000th of a second to circle an entire star. These numbers also set a hard limit on how fast such a star can spin before its own surface is flung apart, and that limit is around 1,000 rotations every single second. And nature actually builds objects that approach this. We call them pulsars, neutron stars spinning hundreds of times a second, sweeping beams of radiation across the cosmos like the lamp of a lighthouse, their pulses arriving at Earth with the steady, relentless precision of the finest clocks ever found in nature. Every one of these properties, The city-sized radius, the half-light speed escape velocity, the millisecond spin, the mountain in a teaspoon, emerges from the same quiet interplay of quantum mechanics, nuclear physics, and gravity that we have been tracing all along. But for all that we now know about what a neutron star is, we have not yet answered how one is actually born. And the answer overturns the entire picture we have been building, because real neutron stars are not stacked together at all. Part 11. Born in the Death of a Giant. Throughout this entire story, we have imagined building a neutron star by hand, gathering neutrons one by one and stacking them until gravity takes over. It has been a useful way to understand the physics, a thought experiment that revealed the forces and the limits. But it is not how the universe actually makes these objects. Nature does not patiently pile up neutrons. It forges neutron stars in an instant, in the most catastrophic events the cosmos has to offer, in the violent death throes of giant stars. And understanding that process reveals one final, remarkable truth about why we are here to ask these questions at all. To understand why a giant star dies the way it does, you have to understand why iron is special, because iron is the trap at the end of every massive star's life. For most of its existence, a star survives by fusing light elements into heavier ones, and every one of those fusion reactions releases energy, which is what holds the star up. Hydrogen fuses into helium and gives off energy. Helium fuses into carbon and gives off energy. On it goes, the star building heavier and heavier elements in a series of nested shells, each fusion step releasing the energy that fights gravity. But this generosity has a hard end point, and that end point is iron. Iron is the most tightly bound nucleus of all, sitting at the very bottom of the energy valley. To fuse iron into anything heavier does not release energy, it consumes it. So the moment a star builds an iron core, the bargain that kept it alive collapses. The core can no longer generate the energy it needs to support itself. It is like a furnace that suddenly finds its fuel has turned to ash that absorbs heat instead of giving it. The star has been fighting gravity for millions of years, and at the instant the iron core forms, it runs out of ammunition. What follows takes less than a second. It begins with a massive star, something at least 8 times heavier than our Sun. For most of its life, such a star is a furnace, fusing light elements into heavier ones in its core, and the outward pressure of all that fusion energy holds the star up against its own enormous gravity. But fusion cannot go on forever. Step by step, the star builds up heavier and heavier elements in its core, until finally it forms a core of iron. And iron is the end of the line, because fusing iron does not release energy, it consumes it. The furnace falters. The outward pressure that held the star up for millions of years suddenly fails. And gravity, which has been waiting patiently this whole time, takes its chance. The iron core begins to collapse. And when the mass of that collapsing core exceeds a critical threshold called the Chandrasekhar limit, about 1.4 times the mass of the Sun, the resistance that had been holding it up, a quantum pressure from its electrons, can no longer cope. The electrons are crushed into the protons, and in that violent merging, protons and electrons combine to become neutrons, releasing a colossal flood of ghostly particles called neutrinos. In a fraction of a second, the core of the star transforms into a dense ball of neutrons, and that new neutron core stiffens suddenly as neutron degeneracy pressure, the very pressure we met in the last part, slams on like a brake. Here is the moment. Picture yourself inside the dying core of that giant star. At the instant everything changes. The iron core is falling inward at a quarter of the speed of light, matter racing toward the center in a catastrophe of collapse. Electrons are being crushed into protons. A torrent of neutrinos is tearing outward through the infalling layers, and at the very center, the newborn ball of neutrons abruptly reaches the limit of how far it can be squeezed. It stiffens, It refuses, and the infalling matter, racing down at enormous speed, strikes that suddenly rigid neutron core and rebounds, like a wave slamming into a wall and recoiling back outward. A shock wave is born in that instant, launched outward through the collapsing star. The shock stalls at first, losing energy as it plows through the infalling matter. But behind it comes the unimaginable flood of neutrinos, and they deposit their energy into the surrounding layers, reigniting the shock, driving it outward with renewed fury. In that half second, a star becomes both a corpse and an explosion at the very same time. The corpse is the neutron star, newly born at the center. The explosion is a core collapse supernova, one of the brightest events in the universe, briefly outshining an entire galaxy. And that explosion does something profound. It takes all the elements the star forged over its long life, the carbon, the oxygen, the iron, and it blasts them out into the galaxy, scattering them across enormous reaches of space. Those elements drift through the cosmos, mixing into clouds of gas and dust, and from those enriched clouds, new stars and new planets eventually form. The carbon in your cells, the oxygen you are breathing right now, the iron in your blood, the calcium in your bones, all of it was forged inside ancient stars and scattered into space by exactly this process, the bounce and the shock and the supernova. You are, quite literally, made of the debris of these events. It is worth lingering on the role of the neutrinos, because they are the strangest and most overlooked players in this drama. Neutrinos are ghostly particles that barely interact with anything at all. Trillions of them are passing through your body every second, streaming out of the sun, and you never feel a single one, because they slip through ordinary matter almost as if it were not there. A neutrino could pass through a wall of solid lead many light years thick and have a fair chance of emerging untouched. And yet, at the center of a collapsing star, something happens that happens almost nowhere else in the universe. The infalling matter becomes so unbelievably dense that even neutrinos, those particles that ignore everything, can no longer pass through freely. They get caught, they pile up, and in getting caught, they dump their colossal energy into the stalled shockwave, and that is what revives it and drives the explosion. A core collapse supernova is, in a strange sense, powered by the one moment in cosmic history when the universe builds something dense enough to stop a neutrino. The very particles that normally ignore all matter become, for a fraction of a second, the hammer that blows a star apart. And consider what that explosion actually accomplishes. Over the long life of the star, fusion built up the elements step by step, hydrogen into helium, helium into carbon and oxygen, on up to iron. But those elements were locked away inside the star, useless to the rest of the cosmos. The supernova is the delivery mechanism. It takes everything the star made and hurls it outward into space at thousands of kilometers per second, seeding the surrounding clouds of gas with the building blocks of everything to come. Some of the very heaviest elements, the gold and the silver and more, are forged in the violence of the explosion itself, or in the collisions of the neutron stars it leaves behind. Without these explosions, the universe would be a thin soup of hydrogen and helium and almost nothing else, with no way to assemble anything as intricate as a rock, a planet, or a person. The supernova is not just the death of a star. It is the event that makes the chemistry of life possible, scattering the necessary ingredients across the galaxy so that, ages later, they can gather again into something new. But here is the part that should stop you cold. This entire chain, the bounce, the shock, the explosion, the scattering of the elements, only happens because neutron stars are allowed to exist with masses greater than the Chandrasekhar limit. It is the formation of that stiff neutron core, able to hold itself up and provide something for the infalling matter to rebound against, that creates the bounce in the first place. If the maximum possible mass of a neutron star were lower, if the rules of physics were just a little different, then collapsing cores above 1.4 solar masses would not pause to form a neutron star at all. They would slide straight through, collapsing directly into black holes, with no stiff core to bounce against, no rebound, no shockwave, no explosion. And without the explosion, there would be no scattering of the heavy elements. They would vanish behind the black hole's horizon instead of seeding the galaxy. No dispersal of carbon and oxygen and iron means no enriched clouds, no rocky planets, no chemistry of life. It means a universe that builds its heavy elements and then buries them forever, a sterile cosmos. The narrow window we found between the minimum mass and the maximum mass of a neutron star is not a piece of astronomical trivia. It is one of the quiet conditions that made a universe capable of building planets and chemistry and us. Part 12. The window we live inside. So let us return, at the very end, to the question a child could ask, the question we started with all those minutes ago. How many neutrons can you stack before reality collapses? We have followed it through the war inside the atom, through the defeat and the resurrection of gravity, through quantum ceilings and back-of-the-envelope mathematics and the deaths of giant stars. And we are finally ready to give the full answer. And the answer, it turns out, is not a number at all. It is a window. Stack just a few neutrons, and the strong force binds them happily. But quantum mechanics, through the Pauli exclusion principle, caps the pile before it can grow large, forcing each new neutron higher in energy until they boil away. Try to keep adding more on that path, and you simply cannot. The road through the strong force runs out of room. So you switch strategies and pile on mass instead, enormous quantities of it, until the weakest force in the universe finally accumulates enough to matter. And once you reach roughly 1/10 of the sun's mass, gravity takes over and binds the neutrons into a star, crushing matter to a density at which a single teaspoon outweighs a mountain. But keep adding more even then. Push past about 2 or 3 times the mass of the sun, and gravity stops being your ally. It grows so overwhelming that not even the quantum refusal of the neutrons to share their states can hold it back. The degeneracy pressure fails, the structure collapses through itself, and you are left with a black hole, an object so dense that not even light can climb back out. That is the window. Bounded below by gravity too weak to bind, bounded above by gravity too strong to resist. Below it, your neutrons disperse into nothing. Above it, they vanish behind a horizon. And only in the narrow band between, only inside that window, does something stable and luminous and extraordinary get to exist. Just keep adding more, our innocent instinct told us at the start. And now we know where that instinct leads. Add too few, and there is nothing. Add too many, and there is darkness. Everything a neutron star is, lives in the gap between. Think back over the journey we have taken to reach this window, because the path itself is part of the marvel. We started with a child's question about stacking neutrons, and we found a war inside every atom, protons repelling each other with the force of suitcases held at arm's length. We watched gravity get laughed out of the room, beaten by a factor with 36 zeros, the weakest force in the universe dismissed as hopeless. We met the strong force and its short reach, and we saw the neutron reveal itself as the perfect glue, only for quantum mechanics to slam the door with the exclusion principle. And then we watched the most remarkable reversal in all of physics, as gravity, that humiliated, dismissed force, rose up through nothing more than patient accumulation and seized control of the entire structure, binding it into a star, and then, pushed too far, crushing it into a black hole. The weakest force in the universe turned out to be the one that writes both the beginning and the end of the story. And the answer it left us with was never a number, it was a window. That is the thing to carry away from all of this. When you ask how many neutrons you can stack before reality collapses, you are not really asking for a count. You are asking about the narrow range of conditions under which the universe permits a certain kind of object to exist at all, bounded below by gravity too feeble to bind, and above by gravity too fierce to resist. Almost everything interesting in physics turns out to live in windows like this, in the narrow bands between too little and too much, and a neutron star is one of the cleanest examples there is. It exists only because the laws of nature happen to leave a gap between the two ways gravity can defeat it, and that gap, that window, is not a detail. As we are about to see, it may be one of the quiet reasons there is anyone here at all. And here is the thought I want to leave you with, the one that turns this from a story about exotic physics into a story about you. That window is not just where neutron stars live. It is, in a real sense, where we live too. Because the universe needs that window to sit exactly where it does. If the maximum mass were just a little lower, if the ceiling of the window dropped below the Chandrasekhar limit, the bounce that powers supernovae would never happen. The heavy elements would never scatter. There would be no enriched clouds, no rocky worlds, no carbon for cells, no oxygen for breath, no iron for blood. There would be no chemistry complex enough to build a living thing, and no living thing to wonder about any of it. The fact that you exist, that you are here, listening, thinking, made of atoms forged in dying stars, and flung across space by the bounce of a newborn neutron core, depends on the width and the placement of that narrow window between too few neutrons and too many. Let that settle slowly, the way the best ideas do when the lights are low and the day is finally done. The atoms that make up your body did not begin here. The carbon in the cells that are listening to these words, the oxygen moving through your lungs right now, the iron riding in your blood, the calcium that holds you upright, were all assembled inside ancient stars that lived and died long before the earth or the sun existed. And the only reason any of those elements escaped the stars that made them, the only reason they were not locked away forever, is the bounce, the sudden stiffening of a newborn neutron core, the rebound, the shock revived by a flood of neutrinos, the explosion that scattered those elements across the galaxy so that ages later, a cloud of that enriched dust could gather itself into a sun and planets and eventually into you. And that bounce only happens because the window sits where it does, because neutron stars are allowed to exist above the Chandrasekhar limit, because gravity's ceiling is high enough to leave room for them. Move that ceiling and the bounce never comes, and the elements stay buried, and the story that leads to you never gets told. You will never stack a single neutron in your life. No one ever will. The construction project we have spent this whole time imagining is one that nobody can carry out. And yet the answer to whether it could be done at all, the answer to how many neutrons you can stack before reality collapses, is woven directly into the fact that you are here to ask the question. The iron in your blood, the oxygen in your breath, the calcium holding you upright, were all scattered into the cosmos by the very events we have been circling, and that scattering only happens because the window sits where it does. You are not observing these violent, beautiful objects from some safe distance. You are made of what they threw away. The construction project you will never carry out is, in the end, the one that built you. And somehow, against all the odds, in the gap between too little and too much, in the narrow window where reality does not collapse, here you are, awake and alive and wondering. And that, perhaps, is the most marvelous answer of all.